In 1632, Galileo Galilei published a groundbreaking idea, one that would reshape our understanding of motion forever. He called it the principle of relativity. And at its heart lies a beautifully simple question. How do you know if you're really moving? Before Galileo, the world followed Aristotle's view that being at rest was the natural state of all things. Objects moved only when pushed and stopped when left alone. But Galileo saw something deeper. He argued that motion is relative. If you are inside a closed room moving at a constant speed in a straight line, no experiment you perform inside that room can tell you whether you are moving or standing perfectly still. To make this vivid, Galileo proposed a famous thought experiment. Picture yourself in the main cabin below the deck of a large ship. Inside, you have butterflies flying around, a bowl of water with fish, and a bottle dripping water into a vessel below it. When the ship is at rest, docked in the harbor, the butterflies fly freely in all directions. The fish swim with ease, and each water drop falls straight down into the vessel. Now the ship begins to move, smoothly and steadily across the sea, with no rocking or swaying. Here is Galileo's remarkable observation. Everything inside the cabin behaves exactly the same. The water drops don't fall behind. The butterflies don't struggle to keep up. The fish swim just as before. Why? Because the motion of the ship is shared by everything inside it. The air, the water, the butterflies, they are all moving together. Inside the cabin, the physics is identical whether the ship is sailing or standing still. This was Galileo's great insight. There is no experiment you can do inside an inertial frame that reveals its motion. There is no absolute rest, only relative motion. Now let's explore the mathematics behind Galilean relativity. To approach this formally, we need to move beyond intuition and define it through the lens of classical space-time geometry. Galilean relativity, stated precisely, is the claim that the laws of mechanics are invariant under a specific set of transformations, the Galilean group. In classical mechanics, we assume a four-dimensional space-time structure with two absolute quantities that are the same for every observer. First, absolute time. The time interval delta t between two events is identical for all observers, no matter how they move. Second, absolute distance. The spatial distance delta r between two simultaneous events is also the same for everyone. These may seem obvious, but they are assumptions. And as we'll see, Einstein later showed they break down at high speeds. Now let's write down the Galilean transformation. Consider two inertial frames, call them S and S prime. Frame S prime moves with a constant velocity v relative to S, and their origins coincide at time zero. The transformation between their coordinates is beautifully simple. Time is unchanged, t prime equals t, and position transforms as x prime equals x minus v times t. That's it. Time is universal, and positions differ only by the distance the moving frame has traveled. From these equations, we can derive the velocity addition rule. Taking the derivative with respect to time, u prime equals u minus v, where u is the velocity of an object in frame S, and u prime is its velocity in S prime. This is the classical addition of velocities. A ball thrown at 20 meters per second on a train moving at 30 meters per second appears to move at 50 meters per second to someone on the ground. Now, here's the heart of the relativity principle. Newton's second law, F equals ma, must retain its form in every inertial frame. Let's prove this. Differentiate the velocity equation one more time. Since v is constant, that's what makes it an inertial frame. Its derivative is zero. This gives us a prime equals a. The acceleration is identical in both frames. And since mass is assumed to be an invariant scalar, m prime equals m, it follows directly that f prime equals f. Force is the same in both frames. Newton's laws hold identically in S and in S prime. No mechanical experiment can distinguish between rest and uniform motion. At a deeper level, these transformations form an algebraic structure called the Galilean group. A general Galilean transformation can be decomposed into three types of operations: rotations, rotating the spatial axes; translations, shifting the origin in space or time; and boosts, the key one, moving to a frame with a different constant velocity. Together, these form a 10-parameter group. Galilean relativity, in its most elegant form, is the requirement that the Lagrangian of a closed mechanical system remains invariant under this entire group. So what is the lasting significance of all this? Galileo's principle of relativity didn't just reshape classical mechanics. It planted the seed for one of the greatest revolutions in physics. When Einstein developed special relativity in 1905, he took Galileo's principle and extended it. Einstein's insight was that not just the laws of mechanics, but all laws of physics, including electromagnetism and the speed of light, must be the same in every inertial frame. This required replacing the Galilean transformations with the Lorentz transformations, where time is no longer absolute. But the core idea that there is no preferred frame of reference, that idea is pure Galileo. And the story doesn't end there. In quantum field theory, the principle of relativity is elevated even further. The requirement that physical laws remain invariant under transformations, now the Poincaré group in relativistic physics, is a foundational axiom. It determines the very structure of particles. Their mass, spin, and quantum numbers all arise from how fields transform under these symmetry operations. From a ship's cabin in the 1600s to the quantum vacuum, Galileo's simple observation echoes across 4 centuries of physics.